There we go. All right. Sorry for a little bit of delay there, folks. Still trying to get myself all squared away. Yes, I like winding Tesla coils when I sit around and watch stuff too. I find it very therapeutic. So today I'm going to share some of the more recent stuff that I've been trying. I've been going through Alexey's old videos looking for any clues based upon his original process of coming up with the Graviflyer, and a few important things that I observed that I had seen before and forgotten, and now I'm remembering. So in some of Alexey's earliest videos, he used a couple different methods. One of the first ones was the bottom disc. He had these magnets on the underside. Basically, this disc was flipped over. These things were mounted on the underside and they were pointed down. He also had another one where he has magnets on top and bottom. And in those instances, they were both pointed in the same direction. I think it was both up like this. And then in another instance, he even mentions that he uses steel, not aluminum. He uses steel for the spinning discs. And in all of those cases, the Graviflyer still lifts or at least tips over on his shop floor. So I think that's really valuable data, because if indeed he is able to get this thing to fly using different configurations with the magnets. Oh, another one. So it's like his first indoor in his living room video that he posted, and the top has like this red plastic on top. The top rotor for that thing is like way up here. Like it's so far away from this disc, and yet the thing is lifting and flying. I think that alone is like huge, because all things being the same, how do you get this so far away that there's no interaction between the eddy currents of these two discs when it's that far away? Yeah, it's wild. That's all I can say. Anyways, so I had this disc here that I built for a previous test. I think its diameter is like, I want to say about 1/2 inch less than the diameter of the disc that I was using for this bottom one, but I don't care. I'm just doing like a little quick test here. So this one, instead of 6 magnets, I've used this for a bottom rotor a while back. Instead of 6 magnets, I squared that, so I have 36 magnets, all in the same polarization, right? North up, so north up. And these are alternating in 42 and 52. My thinking with the alternating strengths there is that if you have all the same strength, it's going to be a uniform eddy current there. And I don't think I want a uniform eddy current. I think I want to have that eddy current have some undulation to it, have some pulse power, if you will. So I just put this on like the other night, and I've only done some preliminary spin tests with it. And you get some interesting vibration stuff with it. So, without any further ado, I'm going to just spin this thing up. We'll watch a test, and then I'll get back to questions after I've done some spin tests here. Turn it on. Get my RPM measurements ready to go. And actually, this is terrifying, because these little magnets, when I spun it too fast in the past, they just shatter and they fly off, and it's, I mentioned, terrifying. There we go. There we go. Get my frequency. All right. So right now I got 21.8 hertz for the top, 22.8 hertz for the bottom. So there's a difference of about 60 RPMs right now between the top and the bottom, just based upon the position that I have these in the eddy current interactions that are happening. So what I want to do is, first I'm going to start slow, a little slower. I'm going to get right below that point where it's like vibrating hard, right? Because that's what Alexey does. He doesn't seem to have huge, nasty vibrations going on. While it's spinning like that, I'm going to take some magnetic field measurements. There you go. So using this guy, which is a little Gauss meter probe, I was doing some magnetic field measurements earlier this week, and I made some observations there. So the magnets from this bottom disc, when nothing is spinning, when everything's just sitting completely stationary, nothing's happening, directly above those magnets on this disc is where the magnetic field is like the strongest, and it's a super small point. And with these magnets that have a surface magnetization of like 2200 Gauss, at the distance of, I think I had a 22 or 25 millimeter spacing, the strongest point on the top side of the center disc was like 475 Gauss, right? But it's a really tiny point. But then as soon as you start spinning it, that magnetic field, that eddy current in there, it like spreads that field around, it smears it around. And your magnetic field strength on this disc will pretty much top out at about 25, 26 Gauss, maybe 30 Gauss around there. It's not much. But long ago, I observed that that magnetic field strength of the eddy current does increase a lot when you apply the high voltage and when you apply the Tesla coil. It can double or triple that. I think it goes up to like 80 Gauss, maybe 100 Gauss tops once you have everything turned on. Yeah, so magnetic field measurements. So I like testing it just at the mid plate. Oh yeah, we're getting way higher strengths than I was getting before, which I would hope since I have all these magnets, these extra magnets. All right, so it's looking like I'm sitting at about 58 Gauss now. Okay. Now for the bottom, can I do this without destroying my probe? So now I'm doing the surface of the bottom side of the mid plate. It should be pretty close, but slightly stronger. 59 Gauss. All right, so pretty much the exact same thing. So we're sitting right around 60 Gauss or 6 millitesla. There we go. Yeah. Let me go through some questions here real quick before I go into the next steps. Here we go. BT7274, you almost got your frame. You got the frame built and the wiring harness. Now extra parts coming in. That is awesome, dude. Congratulations. It feels really good once you have the thing ready to go. It just every time I build a new one of these, I'm so excited. I can't wait to start testing the new version and see all the differences that it makes. So right now I have this piece of electrical tape that is come unstuck, but it doesn't really affect operation too bad, so I'm just going to leave it for now. I see people are asking for some Tesla coil stuff. I'm going to do some Tesla coil stuff after I do this test here, so probably about 15 minutes, 20 minutes maybe. So now what I want to do is I want to go from very slowest, find the minimum speed that it goes when it starts vibrating. And then I will ramp up through the speeds, and I'll find at what speeds does it shake a whole lot. or at what speeds do I get really strong beat frequencies, vroom, vroom, right? Because those beat frequencies seem to be pretty important based upon observations on the spectrum analyzer. All right, I'm getting some good wobble there. Some good wobblage. Let's see if I can observe if I'm getting beat frequencies in the eddy current. Let's go 50 megahertz. Amplitude's way down. Here's my probe. I want to connect you there. All right, so problem is if I connect my probe to the actual center disk, it likes to fall off when it vibrates a lot. Also, the amplitude, even though it's a 10x probe, the amplitude is just so high that I end up having trouble seeing all my stuff. But for now, since I'm just doing speed tests, I'm not doing any Tesla coil stuff, it's fine to connect it to there, I hope. So let's get my amplitude going right here. There we go. All right. Now I'm going to go up through my spin test, and I'm going to watch my spikes on here. I'm going to see if I end up starting to get like moving humps either up or down on there. There you go. So basically, I'm just going to increase my PWM one at a time. Let the speed creep up. It takes about 20 to 30 seconds after I make an adjustment for it to actually start getting close to where it'll settle. Now, granted, if I turn on the Tesla coil and the high voltage, it will amplify, it'll accentuate the wobble of everything, but I don't want to do that when I have my probe connected to it. So for now, I'm just relying upon minor wobbles and vibrations rather than going for major ones, because I always know that I can amplify the minor ones. Now I'm starting to get somewhere. Let me get my microphone a little closer for you guys. I apologize. There you go. That should make it, hopefully, a little bit easier to hear. That is the good beat frequency that I'm looking for. See all that flutter? Oh no. Got some. The nuts are coming loose. There we go. That's a lot better. It's vibrating kind of like a drum. And right now that's at about 22 hertz for the top, 22.8 hertz for the bottom. Really speed it up. I'm scared to go much faster than that. And that we were sitting at just about 23.8 for the bottom, 23.2 for the top. So what I really like to see is, what I'm looking for all this is, once you've got this vibration stuff going on, that's when you can start tweaking high voltage and RF and ultrasound. And the goal is to get it to go from being a pulsating to being a steady, right? And then once it's a steady, my thinking is that you can then start extracting some of that vibration into lift. That there's a lot of theories on how this thing might work. That's just the one that I am considering right now. That's why it's important that I should tighten my nuts. Also, I don't know how well this. Yeah, the camera doesn't really capture it super well. My eyes can see it pretty well though. The vibration isn't just like in one spot and then another spot and one spot and another spot. It's actually traveling around the perimeter of the disc. Like I can watch these vibrations walking around the center disc, which I also think is quite interesting. All right, now I'm going to take off my probe, and now I will add in some high voltage, some RF, some ultrasound, and we'll see where this thing goes. My wires sitting right up against my high voltage wires. I found that these high voltage wires, even though there's insulation, the high voltage wires can still send like the electric field through their insulation strong enough that I can get interference. Turned up my high voltage, so I started at 10 volts in on my power brick here. I'm not sure if the magnets on the top one are going to affect the arcing likelihood. Hope it doesn't arc. It scares the crap out of me every time it arcs. Slowly increase my high voltage. You can see, like, it's got some good, like, it's twisting back and forth now, too. If I can get that little in there. Drew from Florida ended up talking to a couple of us after the last APEC, and we were kind of talking about his technology a little bit. We were talking about virtual particles and how virtual particles might be related to inertia. So there might be a way to like dampen inertia by creating a uniform sphere of charge. Just giving him ideas on other things that you might be able to do with the technology, picking his brain to see what other applications this technology might have. And then with regards to the Graviflyer, basically I came away from it with, I need to talk to their head electrostatics guy from NASA, Charles Bueller, who is interested in the Graviflyer, but they got a lot of other stuff that they're working on right now because they were just featured in the debrief, and like, you know, tens of millions, 100 million, I don't know how many people have read that article now, but it's a buttload. So they got a lot of stuff on their plate right now. So I don't think Charles Bueller has a whole lot of time to dedicate to explaining how he thinks the Graviflyer is working. But the gist of their whole thing is electrostatics, right? So you're not using any magnets. It's it's just using high voltages, and those high voltages end up sending charge into a medium or across the medium, and as that charge builds up inside the medium that it's supposed to go through, eventually you get propulsion. That's like the gist. So he's saying like maybe I'm shoving charge into the center disk somehow. Maybe the eddy current is changing the permittivity of the material, right? So you're getting a difference in charge migration or flow of charge, which might account for the lift. I don't know, because their thing, they've iterated for so many years and so much effort into their iterations, and they are now producing unity of thrust, right? They're producing like 300 milligrams of thrust for a 300 milligram thing, which is awesome. But Alexey's produces more than unity of thrust, and it's built out of scrap parts. So, and it's not using all these fancy things like they're using. They're using all sorts of crazy materials. Alexey's not using crazy materials. He's using scrap parts. I don't want to touch the metal when I got high voltage on, because even though the frame is not charged yet, I don't have the test coil on yet, the high voltage charge from the spinning discs still creates electrostatic potential on these surfaces, so you can still get that. Not as bad, but you can still hurt it. Alexey, when he touches his, he often has like a big rubber thing on the top of his somehow, or something that he can touch that's not metal. So whenever he's pushing down on the Graviflyer, there's a couple of points where he'll touch the frame, but I don't know, he's ballsy. It's not that ballsy. All right, let's turn up my electrostatic just a little more. Okay, that's about the most I can do before it's going to want to arc. Now I will connect my back up here. Let's see on here. So right now my probe is actually connected to this optical sensor. So that's part of the ramping up and down that you're seeing. But part of that also is electrostatic noise that's entering these lines. So, turn on our testing coil now. Turn that on. Now I can turn my testing coil on. There we go. And now I'm seeing the ring light on my camera is starting to go wonky. So I got a bunch of RF. The high voltage from the flyback, when combined with the Tesla coil, you get a lot stronger electromagnetic interference than just the regular Tesla coil by itself. Ramp the Tesla coil up and down a couple of times. All right, let that stabilize for a second. Read some messages, and then I will apply ultrasound. Let's see. Yeah, so for my safety barrier when I'm testing like this, didn't want to do it on camera because I think it looks kind of dumb. But what I'll do is I'll take my chair, and I'll like hold my chair up as a barrier and like peek over the top. Super safe, guys. Super safe. Let's see. BT7274. So yeah, for the longest time, I ended up insulating the rods, the vertical rods from the center disc. But Alexey never did that. He never did that. He always had everything electrically connected. And in some cases, he even electrically connected the center disc to the top disc with like a brush. You can see that in his indoor video with the Graviflyer with the red top. He like stops it after it's lifted and looks close at it, and very briefly you can kind of see he had like the high voltage brush for the top disc was like screwed on to the center disc. So like there might be a there as well, but yeah, you can insulate it, but Alexey never did. Do you have your ground connected on your oscilloscope? Yeah, the oscilloscope is grounded. However, with the 10x probes, I'm starting to build up some field, I can tell you that much. I don't know how, but I'm starting to get overload on here, and I haven't changed anything. So yeah, it's that buildup of the field. Got to attenuate it a little more. Let's get my frequency down a lot more. I think it's this lowest Tesla coil spike. Oops. Let's go 3 megahertz. Yeah, it's this lowest spike here, which is at 748 kilohertz right now. I think the amplitude of that, every once in a while, it kind of climbs up. And so if I don't have the attenuation on my scope set right, it like overmaxes it out. Also, like I said, the ring light, I don't know if it really shows up. You might see a reflection here every once in a while of the ring light on the camera like change color. It's got a little capacitive touch button on the bottom of the camera. Oh, just changed color again. Let's see if I can hold up something white so the camera so you can kind of see. So I'm just going to hold this up near the camera and see if you can see when it changes color. Get some reflection. Oh no, I got a mirror. That's a lot better. So the camera, let's see if it changes color here. Oh, oops. Okay, well, the Graviflyer just got really smooth all of a sudden. So, oh, I see what's going on. You can't really see it. Maybe you can see it kind of. The high voltage red line going to the top disc, I'm starting to get arcing right at the base of the terminal on that thing. You can kind of see it. Can't get my finger close enough. Right kind of there. It's just a tiny little red thing. Oh, now the ring light just turned off the light of itself. Anyways, I was starting to get arcing. Yeah, I get little tiny sparks inside there, which means that the wires to my the base of the terminal for the high voltage going to the top disc is starting to break down. So I'm going to have to reconnect that terminal. But for now, let's do some static measurements. That's really interesting that it just got super smooth. Like it is super smooth and locked in. I haven't even applied the ultrasound yet. Let's apply ultrasound. So I actually just got some results back from our console guy. And he found some really interesting stuff with the piezo buzzer. Oh man, I'm starting to get this quick little oscillation back and forth. And that's how I know that it's like getting in the real sweet spot where it wants to fly. So I'm just going to pay attention and not talk too much for a minute. Just going to slowly creep through this ultrasound. I'm starting to see really big sparks on that top high voltage terminal, that positive terminal. That could be because it's breaking down. Oh, seeing my ring light camera change. Yeah, I'm getting a lot of interesting effects at the moment for electromagnetic interference. So I've noticed there are certain times where I swear it sounds like the speed of discs changes significantly with changing the ultrasound frequency. Like increasing frequency increases speed of the discs. And it's in the ultrasound, so I can't hear the buzzer, but I know that I'm increasing the frequency of it. And yeah, discs just end up sounding like they're getting faster. Like right there. Like it's not a lot. It's like, you know, maybe 6 RPMs, but it's enough that like you can hear it. Like 6 RPMs per little turn. So eventually, like I think we can change the RPMs by maybe up to 100 RPMs just with ultrasound changes. It's hard to say though because all my electronics don't want to read nothing. So I'm kind of using the ring light of the camera out of the corner of my eye to tell when I got like a frequency that's getting strong EMI. Like instead of using the fluorescent bulb, I can just use my nearby electronics. I'm starting to get singing notes. Todd's saying maybe we should call it our T-Brain. Yeah, I ended up choosing the name Mighty Brain because of 2 reasons. One, I really liked the Mighty engine that Andrea Rossi invented, which is the massive yet tiny engine. And I thought it sounded cool to say that we all kind of have massive yet tiny brains, right? Brains are 3-pound spools of mush that are able to unravel the secrets of the universe. See, that's pretty massive and tiny at the same time. And then I ended up getting really into yerba mate, so I'm like, oh, my tea, like drinking tea brain. And then I wanted to create an Amazon store for selling educational kits. And so I was like, oh, mighty brain for like kids having mighty brains. Oh, I think oh shit. My top disc is about to fall off. I gotta turn this off. Oh shit. You saw it here first, folks. Oh, there we go. I'm glad I saw that. I've had that top disc fall off like plenty of times in the past. And usually when it does, like it's terrifying, but nothing bad happens. Like it kind of just plops down, like kind of walks over a little bit and then drops on the ground. But if I let that happen this time, all those little magnets that I have on there would definitely shatter if it fell on the ground. Yeah. That is unfortunate. I really wanted to get to the point where I could push the button. But it was actually really interesting. Something I saw right before it fell off, that top disc, it wasn't just slowly sliding down. Like once it had gotten loose on there, it was actually kind of like floating up and down on the center shaft, which is really, really interesting. I'm externally processing right now, but like if it's floating like that, if it's getting like an upward push like that, that's lift. It's not lift of the whole thing, but it's lift of the disc. The disc itself is getting pushed up. I don't know if there's equal and opposite forces going on, but yeah, I'm gonna have to go back and review the footage from the live stream and see if that shows up on camera to see if you can observe that up and down movement. It was moving up and down the shaft. I'd say maybe about 3 millimeters. Let me verify that. It's moving up the shaft about, yeah, I'd say 3 to 4 millimeters. About that much, like enough to be noticeable. That is interesting. All right, now I will get back to questions and I will do test coil stuffs. All right, let me go through these. Have you tested to see if your ultrasound, let me turn this over here a little bit. Have you tested to see if your ultrasound is actually transferring through the whole craft? Yes, sort of. So the ultrasound vibrations, the piezoelectric, like the sound, above 20 kilohertz, you're not getting any transfer of acoustic energy through air. Like it attenuates so hard. You're getting like 1% of the power at 20 kilohertz, and you're getting like 0.1% of the power at like 50 kilohertz and 0.01% of the power at like 100 kilohertz. Like it attenuates really fast. Which, fun fact, so bats that use ultrasonic, they use like, 30 to 60 kilohertz, I think, for their echolocation. They're actually screaming insanely loud because you have to with ultrasonic sounds and air. Our ears have just evolved to hear in this range that just so happens to be like the most energy efficient range for sound propagation in air. It's, no coincidence that we hear 20 hertz to 20,000 hertz because the attenuation of sound in air just skyrockets. It's an exponential curve above 20 kilohertz for dampening. I should say exponential curve downward for like the amount of sound that you'll hear, right? How far it carries. So that said, the ComSol guy, he ended up doing all these modelings and simulations of a lot of this, but he focused a lot on the piezo buzzer, and he found something that correlates to something that I found. So I think it was March of last year, I was putting, I don't know, I think it was like 4.5 megahertz through an RF amplifier onto the center disc. And I was going through ultrasound frequencies, and I was watching to see how do my harmonics, how do they change at different ultrasound frequencies, harmonics of the RF on the center disc. And ended up, there was I think it was like 62.7 kilohertz or something. And that was with that craft up there. But at like 62 point whatever kilohertz, when I would turn on and off the ultrasound, I observed that the third harmonic of that RF signal would change. So when I would turn, I can never remember. It's like when I would turn on the ultrasound, it would drop that third harmonic, which was like 14.7 megahertz. It would drop that by 3 dB. It would cut the power in half for the third harmonic when I would turn on the ultrasound at those frequencies. Well, the COMSOL guy found that these piezo buzzers at about 65 kilohertz, very close, give or take, he found that the power transfer to that diaphragm, it doesn't fall off. These are like 2 to 5 kilohertz buzzers. Like that's what they're rated for. They're just regular sound buzzers. And so that's what they're tuned for. So as you go outside of that tuning range, it's not very loud. But these buzzers, they just so happen to have certain sweet spots where they get super loud at specific frequencies. So this thing, it's like its power, its output power of the piezo buzzer, it like drops off significantly as you go higher and higher. And then around 65, it goes really high again, and it starts getting higher again. And then I think by 90, it starts dropping off again. Yeah, so hopefully I'll be getting some good results from COMSOL guy here pretty soon for the rest of the craft and how that all interacts all together. Yeah, lots of interesting stuff with the piezo. Have we tried using slip rings for the plate power? Slip rings for the plate power. I assume you are referring to the high voltage applied to the spinning discs. We have gone through a couple different iterations for applying that high voltage. Alexey's original version uses like these big brass strips that I'm not a fan of because they produce a lot of drag. Here is an example. Maybe I can get it. Here we go. Here's an example of the brass strips that he's using. So you mount this like this, and like the disc just rubs over it, which is like okay, I guess. You're getting contact, but it's extra drag, and I don't know if it's the conductivity of it or if it's the charge carrying capacity of it. I don't know what it is about these brass strips, but when I used them, the overall voltage that I was able to transfer was much less. Like these things topped out at +3, -3 kV, which is poop. It's poop. You need more than that, I think. I mean, maybe. I don't know. Alexey might not be getting above +and -3 kV, but it seems like there comes a time where everything starts building up really fast, and I don't know. Use a mini subwoofer. So actually, I've looked into using different speaker transducer systems for the piezo buzzer. There might be a good reason to use a bigger one, or a more powerful one, but I have a suspicion that the piezoelectric nature of the buzzer is important. I think that the buzzer itself is kind of acting like a little capacitor. And if you had like a speaker diaphragm thing, that's not going to act like that. That's just another electromagnet. That piezo buzzer, as it goes from a compressed state to an expanded state, it's changing the amount of charge that it has, right? It's sucking in charge and it's spewing out charge through every oscillation, right? Just like a capacitor. So yeah, I've looked into, I'm actually using a larger piezoelectric than Alexey ever used. I think mine is like 35 or 40 millimeter diameter right now. And Alexey, I think he used 27 millimeter and maybe used a 35 millimeter at one point. But yeah, I think going bigger with the piezo buzzer might be better. I tried using a stack of piezo buzzers But the problem with that is getting those all in phase aligned together is a nightmare, and their electric fields are interacting, and like you can't do it. You have to use just a single buzzer. Let's see. I gotta scroll way back. Anthony Scott is saying that he's actually had lift before and he knows exactly what caused it in his setup, but he wasn't using a Graviflyer. Anthony, I would be very interested in hearing about that. If you want to shoot me an email over at mightybrain@yahoo, let's talk. He's saying he had the whole power cable floating in the air with partial Van de Graaff, partial AC, and partial negative static. All right. So the cool thing that I've learned about this stuff is when you take an AC signal and a DC signal, right? Static and AC. You are creating a instead of an AC signal that's going up and down above the 0 voltage line, it's like either stacked above the voltage line or below the voltage line, right? You have a DC offset AC signal. And I've seen some documents that suggest that that might be one of the methods that was used in the earliest versions, like the 1950s versions of the UFO, of the reverse engineered, right? The human-built saucers might have been using a DC offset AC signal. Yeah, I could go more into that, but the caffeine hasn't kicked in hard enough for me to really remember enough. Anthony's saying he built a Van de Graaff that had no top load to build positive charge, and that all the charges come from the negative. Side built up around the AC cable, and it started lifting in the air. The Van de Graaff would arc, and it would drop, then repeat. Hey, that correlates with Alexey's thing too. When his Graviflyer arced, that's when it would tip, like it would lose its thrust the moment, not the moment, like within a 2 to 4 second delay after arcing, it would noticeably be losing its lift. Let's see, still going through the comments here. Sorry, a lot of comments to go through. Almost done. Yeah, Anthony, email me. Let's set up a Google Meets or something, a Zoom call. I want to hear all about your stuff. It sounds really interesting. Yeah, so in some of my absolutely earliest tests, I was in a different part of the shop, and I was set up on this workbench over there, and I actually just had a big piece of plywood as a barrier, and I could kind of like peek around the side of the plywood and like watch it that way, and that was pretty good. And then if you just test it on the ground, you know, it's a lot better to take out your ankles than your face, but can't see it down there. You got to bend over. It's not fun. And it's hard to get the camera at the angle where you can see it edge on like this. I think there's a lot of value to be had in this goes for all y'all who are building and testing this. Whenever you do testing, highly recommend keeping a camera running and have that camera pointed edge on, because you can go back through and you can like just fast forward through however long you tested, and you can see what were you doing when you got the thing to rotate or to kind of tip in one way or anything like that. I've had some really good observations made on my videos that are like, 2-hour long testing sessions. And I watch it at like 32x speed. And it's enough that I can go, oh, it's when I was in about that frequency range that I got something to happen. It was when I was at about that speed that I got something to happen. So highly, highly recommend having a setup where you can keep a camera pointed edge on. Also, edge on lets you see how the discs and everything, are wobbling and vibrating, which is valuable. Do you have a Gravito meter? No, I do not have a Gravito meter. I have some good reason why I don't have a Gravito meter, but I might have Charles build me one. I'm not going to build one anytime soon. So if you've looked at the schematic of the Gravito meter, it is a capacitor connected to LEDs. Like that's all it is. Like it's got a potentiometer on it, sure. But like the gist is, the thing is, it's monitoring for high voltage at high frequency, right? And high voltage in the case of his Gravito meter is 1,000 volts because he's using 1,000 volt, I think 50 microfarad cap or something like that. Like it's a really small capacitor inside there. And the gist is that once you get at 1,000 volts difference of potential between the arms of that thing, it stops, storing that charge, and then it ends up making the LEDs like come on. So I want to say, don't quote me on this. I can't remember. I need more caffeine. I want to say the red light on the Gravito meter is indicative that you're getting that 1,000 volts. And I want to say the green is indicative that you are in the ballpark of the frequency on that 1,000 volts. I think that's what it is. Don't quote me. But he adjusts the potentiometer knob on the Gravito meter to like, I want to say to adjust like how strong the electric field needs to be. So he's like taking it from 1,000 volts, like lower and lower and lower. So the 1,000 volts is like the maximum setting. So yeah, if you have actual tools like a voltage meter that can measure a lot more than 1,000 volts, like that's useful. If you got something that can measure the frequency above, a megahertz or whatever that is, that's a lot better data than an LED light going off. So yeah, I don't know. Gravito meter, very, very impressive. I gotta say, I'm super impressed with his ingenuity at coming up with the Gravito meter as, the poor man's version of all this equipment, right? This thing's like $200-300. That thing is like 1,000, 1,200, something like that. So, and he came up with it for like $5. So like, props to Alexey as always. John Paul is asking, why are my Tesla coils so tall? So I was playing around with different Tesla coil windings and stuff. So I have that one really tall one that I can't point at very easily. I have that tall one right there. Is like 5.5 feet tall. And I want to say it was something like, I was using really fat gauge wire too. So what I was doing was I was trying to use the largest gauge wire possible so that I could reduce the resistance of the thing as much as possible and try to get more current. I was trying to increase the current part of the thing in addition to the voltage part of the thing, right? If you decrease the resistance on your Tesla coil, it increases the Q factor, right? It's got less damping if it's got less resistance. So less damping means more resonance, more juice. So that's kind of what I was doing with that. But unfortunately, after I did it, then I did the calculations. Foolish. Turns out that skinny, tall Tesla coils, not great. There's a special proportionality for Tesla coils that makes them more or less efficient. So I managed to make it semi-efficient, but unfortunately it's it's not quite what I need. So I ended up having Charles just make me one of his uniform versions. That's, you know, the 1000 turn or whatever. That is, you know, pretty much exactly like Alexey's Tesla coils. And I gotta say, the performance of this little Tesla coil here is way better than the performance that I was able to get out of my tall Tesla coil. Let's see what else we got. Boskin is saying, after you make it lift, do you plan to have a new version that is more compact and put some of the parts into a single unit? Yeah, so I think once we get this into a state where we can reliably just get it to lift, right? And reliable, I use that very loosely. But if we can get it to lift repeatedly, I have a feeling that we're going to be able to improve upon the design significantly. So the first goal before making it into, you know, a big craft or anything is just to make it into a more powerful craft, right? I don't want to lift 1,000 pound or 1,000 kilogram craft and have it be able to take, you know, a 5 kilo load. Like, that's a lot of effort that I think could be improved upon if I can make 1,000 kilo craft that can lift 100 kilo or more load, right? There's a lot more value in that, because at 100 kilos, you're lifting all of your equipment plus maybe a passenger, or at least a very valuable load up into orbit, assuming that it does not rely upon atmospheric conditions to operate, which we've discussed that too. You might need to create a whole enclosure for this thing and keep atmospheric pressure and air composition inside here, even in the vacuum of space, because maybe there's electrostatic stuff going on. But if that's the case, we might be able to adjust the mixture of the atmosphere around the disks to improve upon. So once again, I think at this stage, we're just all about replication. Then the next step is iteration. And then the step after iteration is actual minimum usable thing, right? I'm still trying to catch up on the comments here. Sorry, still catching up on messages. Daniel's saying he thinks 17,820 hertz, 17.8 kilohertz is for countering the aluminum weight. That's the aluminum resonance in hertz. Okay, so the resonance is very dependent upon so many factors. So the resonance changes if you put high voltage on it. The resonance changes if it's under centrifugal force. The resonance changes depending on how you have it mounted. So like this center disc is very flimsy, right? Because it's really thin and really wide. Whereas the spinning discs are much smaller diameter and of the same thickness. But that means because they're smaller diameter and they have a really large thing in the middle. Can I do this without shocking myself? Yep. Because I have this huge hub in the middle, right? That makes it so that the resonance across this disc is a lot different than if it was, you know, just center hub mounted with a single screw. It shortens the length of the vibration, right? So I'm using a really short string versus a very long string. Let's see. The more force put into the aluminum when it's showing magnetic effects, the more resistant it becomes to the field. I'm not sure which force put into the aluminum you're talking about. Gypsy. Oh, I see the gypsy nurse That's a cool name. Did you print those white braces? If so, where can we print them? I tell you what, I will put up a link. I will put up a link to all of my 3D print files in the Reddit thread. So if you go to Reddit under r/Graviflyer, flyer Flyer, right? So if you go to that subreddit of Graviflyer, I will upload today. I will upload the STL files that I've been using for everything. You might find that helpful. Yeah. After you make it lift, do you plan to have a new version that's more compact? Oh, no, I already saw that one. How do you use an iPhone as a gravimeter? Well, I can tell you that. If you take your iPhone and you hold it too close, it'll start glitching out real hard. That's a Gravito meter. It tells you that you got really high voltage at RF frequencies. I wouldn't recommend it. Good way to fry your phone. Isaac is saying that on the Gravito meter, red is when all your fields are ready and you can turn on the piezo, and then green is ready for takeoff. Yeah, like Alexey talks about how, in some of his videos, he talks about how the Gravito meter is supposed to be used. He says that, yeah, the light has to be green, that you're not going to get lift if the light isn't green. And like I said, I'm not familiar enough with the Gravito meter other than, having looked at its circuitry a bunch, but I have never used the Gravito meter, so I can't tell you. I know Charles has managed to get the light to turn green. That's kind of been the big hold up for, I think, well over a year. Like nobody could even get the light to turn green, but I know Charles has gotten it to turn green. Let's see, more comments. Oh, Plumium saying that your Graviflyer is so close to your equipment, like this stuff, aren't you worried about interference? Kind of, but I'm getting way more interference just through the lines going to the equipment, right? Yeah, I will say I've had my, so this oscilloscope, which is a Rigol or a Regal MSO 5074. It's a touch screen, right? It's a touch screen, which is bad when you're dealing with high electric fields. So there'll be times where I have I'll have something up on the screen that's blocking what I can see. I'm like, oh, I gotta close that, and I try to turn it off, and I'm tapping, and it won't go away. I'm like, shoot, I can't even see my screen, and I can't close it out because it's non-responsive. So yeah, there are times, but I think it is what it is. My cables, my wires, everything's only so long. So I'm not too terribly concerned about it at the moment. And everything, these two pieces of equipment I have are surprisingly resilient. They're dummy proof. If you actually fry or zorch these things, you get some kind of metal. They're student proof. They have all these alarms that go off if you're over voltaging them or too much juice into them. So it lets you know pretty quick that you need to turn up your attenuation or turn down the signal that's going into them, or just disconnect it, right? So you don't fry something. And I've had it beep on me for probably a solid 10 minutes straight. And I'm just I don't care. I've already maxed the attenuation. I don't want to disconnect. I want to keep seeing what signal's on there. And the signal's just blasted up at the very top of the amplitude, but super resilient. So AC genetic jabber saying AC to DC, get quartz wafer 30 centimeter diameter in between 3 or 6 millimeter thick with a bifilar on top of the wafer. Put some thin aluminum under the bifilar and have 2 spark gaps to see some magic happen. Genetic jabber, have you witnessed this yourself in person, or have you seen videos of this, or is this an idea that needs to be verified? Or if somebody's going to claim magic's going to happen, I want some evidence of the magic happening. I'll believe that magic happens once I see some, results of it happening. Sounds interesting, though. I know that Nathan, Old Man Builds, he put a bifilar pancake coil on his center disc, and 1, it made it super heavy, and 2, he had some interesting results from it. I think it was like really interfering with, like, it was really slowing down, or like the magnetic fields coming from the spinning discs or something. I can't all recall what happened with that, but I thought it was a really interesting idea. I will say this, around 2016, 2017, the idea of trifilar windings got into my head somehow, and it never left. And I just saw something from Bedini recently. He's like a free energy over unity energy guy. And he was talking about using trifilar windings for like a special kind of homopolar motor. And that was getting me all sorts of going, because I've been looking for anything that makes good use of trifilar windings. And I haven't found a whole lot. A lot of people just say, well, it's for 3-phase. Well, not exactly. Trifilar windings have a lot more uses than just 3-phase, but yeah. Bifilar have their uses, but trifilar there's magic in there. Gypsy Nurse is saying there's a magnetic field above and below the aluminum center disc, and a strong magnetic field. This effect is created. Interesting. I will say this, earlier this week, I made another interesting observation with my magnetic stuff. So I had just a regular non-magnets for the top disc, right? The normal setup that I've been doing. And since I'm now running both of these motors off of a single PWM controller, it's a lot harder to try to get the speeds of the two matched. When you get the speeds of the two matched, that's when you can get like these runaway effects happen. So I'm all about trying to find ways to make that happen while still maintaining Alexey's methodology. So what I found was his spacing distances seems to be strongly related to trying to get the magnetic field strengths of what's going on here all balanced out so that the two discs spin at the same speed. Well, the bottom disc is creating an eddy current in the center disc. That eddy current is then interacting with the aluminum disc above it, creating a smaller eddy current in that one, which slows it down. Then you've got electrostatic effects, which are interacting with those eddy currents. Well, what I found was I ended up using this spacing block that I've 3D printed to maintain the proper spacings here, right? And I got the distance written on the sides. I don't have to use my micrometer every time. I can just use this little block and go, okay, yeah, I'm at like 21 millimeters. Anyway, so I taped my probe to this spacing block so that I knew exactly how high it was, and I set that, on the disc, on the center disc, and then I went through different speeds with the bottom disc, and I raised this top disc way up high. I went through different speeds, and I was looking to see how the speed affects the magnetic field strength. And what I found was above about 13 to maybe it was 15 hertz, like the magnetic field strength at 20 millimeters spacing just leveled out. Like you throw in more spinny spin, you get no extra magnetic pulley pull. So that was a useful thing. Also, the distance, there's a very sweet spot at like 18 to 22 millimeter height above this disc where when the bottom is spaced at like 25 to 30 millimeters. There's a very small area where the magnetic field just dies. Like it goes from 2 Gauss to 0 Gauss like that. And it just so happens that if you put the top disc right at the spot, right sitting right on that transition zone of the magnetic field strength from the bottom disc, when the bottom disc is spinning, right? Take off, here's what you do. You take off your top disc, you spin just the bottom disc, and you use your little magnetic probe, get off of AliExpress for like, I can't remember how much this was. Maybe it was like 30 or 50 bucks. Might have been a little more, but and you find at what height, when this bottom one is spinning, at what height does the magnetic field completely die out? And that right there, minus a millimeter or two, right? A millimeter or two closer than that, that right there is where you should set the spacing for your top disc if you want to get the 2 discs to spin at the same speed. Thought that was a pretty useful observation this week. Weren't Alexey's top and bottom support bars conductive? Sort of, kind of. So the support bars themselves were conductive, right? So they're made of aluminum. I think it was like, I don't think it was 80-20. I think it might have been like closet roller rails that look like you screw into the floor. I think he was using some kind of version of those for his rails here. Anyways, but those things are screwed into plastic for everything else over here, right? So it's like the center disc, the vertical rods, and the cross struts, cross members, those are conductive. But that conductivity stops once you get to the motor mounts. So I don't know how much that really affects the operation of anything to have these cross members conductive. It might, because you got electric and magnetic fields running around like crazy. But yeah, I don't think that was a make it or break it type thing. You want to use a dielectric with a high K factor like barium titanate. That's if you're doing a TT Brown. This ain't a TT Brown. TT Brown wasn't dealing with magnetic fields. TT Brown was dealing with just high voltages. And this thing, some people think that this is just a specialized TT Brown thing. TT Brown, his device would barely produce like a gram at 30 kV. It didn't produce like legitimate thrust until he got up into like the 150 plus kV range, right? To get any real noticeable thrust, you were above 50 kV. This thing is producing newtons of thrust, right? It's producing 1.5 kilograms thrust at 30 kV or less, right? And Alexey was using all conductive stuffs, right? So if this thing's a TT Brown thing, it's very unlike any other TT Brown thing. Yeah, that's what I'll say about that. The effect in aluminum is paramagnetic in nature. Important to make distinctions. Yes, absolutely yes. So for everyone who's working on this thing, you should definitely understand the difference between paramagnetism and diamagnetism. Paramagnetism, you get eddy currents. Diamagnetism, it doesn't let the magnetic fields penetrate, like pushes them out, right? The fact that you're getting eddy currents in all of these things means that you could be having like these lines of magnetic flux that are starting to align in between. It's like moving lines of flux that could be aligning with the magnets, right? Or in between the magnets. Mike Gamble was saying that he thought, let's see if I can tilt this so you can kind of see. There we go. He thought that for these magnets here on the bottom disc, that it was kind of like an egg shape of eddy current in between each of these magnets, right? So you get an egg shape in between, and then you get like an oval shape from the magnet to the center, right? And it's all these interacting, these cross-flowing eddy currents in this bottom disc that were really important. So his early on recommendation to us was you need to bring the magnets on the lower disc closer to the center, which will increase the magnetic field strength of those counter-flowing eddy currents in the bottom disc. I did that, and I think I tested with that for like 2 or 3 weeks. I didn't really see a whole lot. There might be a there, but I don't know. On all of Alexey's things, he always has these magnets, like usually pretty flush with the outer edge, if not maybe a little past. Like they're usually pretty close to the outer edge. They're usually not like way inside the center with a big old gap going out, you know, towards the edge. Ooh, Daniel Foster saying sex filer windings. 6-filer has benefits. That would be interesting. If you took 2 trifilars and you had those interacting against each other, that might be a thing. I mean, y'all probably know Tesla had this obsession with 369, or so the story goes. I don't know. A good chunk of what I see and read and hear about Tesla is like hearsay because, you know, autobiography wasn't exactly there. And I know I've seen some repository of his, not just his patents, but like his notebooks and stuff. But there's not a whole lot there. A lot of it was confiscated. What's the RPM at 20 hertz? So for RPM, hertz to RPMs, you just multiply by 60. So 10 RPMs is, or 10 hertz is 600 RPM. 20 hertz is 1200 RPM. So the RPMs where the thing kind of levels off, being, you know, 15 RPM, or I mean 15 hertz would be 900 RPM. What are the messages we got here? Electroplating thin layers would work as well. We've actually talked about electroplating these things. I think it would be really cool. I found some of this purple gold. So it's like gold nanoparticles that you can use to coat stuff with. I think that would be very interesting to coat all 3 discs with gold nanoparticles. The problem is that if you have these any brushes, right, the way that you're putting the high voltage on the disc, you got to be careful that it's not going to scrape off that super thin layer of gold particles. But yeah, if you have gold nanoparticles on your disc, it should increase. I want to say it should increase the capacitance a bit. Torman saying he can't do the thing off the ground because he tried to glue quartz powder on his rotating disc to create a frequency, but then he moved back to the basics. Okay, story time, guys. If you haven't heard of this, there is a super old, like 2,000-year-old story about a flying saucer that most of you probably don't know about. Some of you might, but let me story time with you guys because I love this story so much. So it's an old Irish story about this guy called Mog Ruith, or Mog Roth. The way the story goes, this guy was a wizard who lived around like Jesus time, and up in Ireland, and he was supposedly like basically a tall white. Like this guy was super tall. Supposedly he lived through like 20 different kings, right? So he was super long lived. He was like a Merlin predecessor. I think supposedly Merlin learned from him. Anyways, so Mog Ruith, he ended up basically building a flying saucer with the help of Simon the Sorcerer from the Bible. It's all story, but there's just like the Vimanas where you get like these little like nuggets of stuff. There's nuggets in the story about how supposedly this thing went, and there's some of the Roman centurion like flying saucer stories line up with the Mog Ruith stories from very far away, right? So there's some there. So anyways, basically Mog Ruith was he wanted to build some kind of flying craft. And in order to do that, he knew that he had to go down and see Simon the Sorcerer down in the Middle East, right? And so the way the story goes is he went down there, he goes to King Herod saying, hey, let me see like your head sorcerer dude, this Simon the Sorcerer guy here, he can help me with what I need. And the story goes, King Herod's like, yeah, but I'll hook you up, but you got to do me a favor first. I got this guy in jail. I want you to go behead him for me. It'd be politically bad. If I behead him, I need you to go behead him. He's like, okay, sure, whatever. And so then Mog Ruith goes to the prison, sees John the Baptist in jail, and goes, well, I can tell you're probably an innocent guy, but I got business. I got to do stuff, so sorry. So chops off John the Baptist's head, brings the head to Herod. Herod's like, cool, thanks. Simon the Sorcerer, I'll bring him by tomorrow. You go and sleep at my place. So Mog Ruith ends up finding Simon the Sorcerer. They end up working together for 2 years to build this flying craft. And for reference, Simon the Sorcerer, who is mentioned in the book of Acts of the Bible, he was known for, in other texts, he was known for levitating. Like he was one of those human levitation stories, right? And he could like levitate on command, and he did all the time. And supposedly that's how he eventually died, is he was like levitating 70 feet off the ground, off of one of these Roman Colosseum like pillars. And 2 of the disciples, Peter and Philip, I think, were like on the ground, like, demons, be gone! And it like messed up his concentration, and boom, falls to the ground, breaks both of his legs, dies the next day. That's Simon the Sorcerer. Anyways, the nuggets to take away from the Mog Ruith story. It said that he had, it was called like the spinning wheel or something like that. And it had electrum, which is gold and silver alloy. It had an electrum ball at the top of it, kind of like the flying saucers that we see that have like the antenna ball thing on the top center thing going on. It had an electrum ball on the top. It had 2 oxen that were inside, like turning the wheel inside, right? And I want to say I found another source that said that it used quartz, right? That's why I'm talking about it, is because this guy is talking about quartz in the chat. So, okay, you got a top load of gold, silver alloy, right? You got quartz, which is piezoelectric, also birefringent, and you got 2 oxen that are turning something inside. So my guess for how that thing supposedly worked is the 2 oxen were turning these huge, I did the calculations a few years ago. They were turning these huge like quartz discs that had been super well polished, right? It was like grinding stones, right? So they were turning one quartz disc against the other quartz disc. And I want to say if you put like, what was it, like sand or something in between the discs, like you can really increase the amount of triboelectric charge that you can get by the grinding of these discs. And then you can feed that triboelectric charge, you know, up to different spots to be able to get this super high difference of potential. Anyways, for anyone who hasn't read the Mog Ruith story, it's a trip. It totally reads like a legend, but I find it super fascinating. Anyways, that's enough story time. Can I get in contact with Sal Pais at all? I saw you guys live with him. His insight would be great, although he's very concerned about educating the enemy. Yeah, no, I have talked with Sal about the Graviflyer, and he was, what's the right word? He was indifferent. He was indifferent. He was neither for nor against. He said that I want to say, I think I'm remembering this right. I want to say that he was also able to appreciate some of the similarities, like I was saying, how you got, rapid acceleration transients of charges, right? The vibrations and the stuff going on here that, yeah, there's some overlap there. But he really did not want to talk about his heme-fig experiment much. He talked about it a little more like off camera or off air, I should say, off recording. But yeah, basically his experiment is what led to him being able to create all these different patent ideas, right? But as far as like actual actionable things that have happened from those patents, I don't know. I don't know if actionable stuff has taken place. It's been super dark. But yeah, all of his patents, as far as I know, came from that heme-fig experiment. So for those who don't know, I think that you can find all the documents for the heme-fig experiment, like on the debrief or something. But yeah, for how that overlaps with the Graviflyer, it's only a partial overlap. So he didn't have a whole lot of extra insights. I think Charles Bueller probably has a lot more insights, being the like top electrostatics guy for the top space agency in the world. Yeah, I think his insights would probably be, for this particular thing, would be a little more valuable. I haven't even gotten to the Tesla coil stuff yet. I need to get going on Tesla coil stuff here for you guys. Oh, cool. A lot of you guys know about the Mongrel story. Yeah, I love it. Basically, you get from Jesus to Merlin with flying saucers in between. That's how I read the Mongrel story. Is Jesus has, cousin John the Baptist and disciples. The disciples end up interacting with Simon the sorcerer. Simon the sorcerer ends up wanting to join them, and then decides that they all decide to hate him. And so then he goes off and he helps Magruth build a flying saucer to scare off all the Romans that were trying to invade. And then Magruth ends up training Merlin. So you got Jesus, disciples, Simon, Magruth, Merlin. Flying saucers in there. Can quartz be turned into a liquid magnet with a nano coating? I'm thinking about a video someone was making a black blob with ferrous metals, I think. Black blob with ferrous metals. You're talking about ferrofluid, which is funny because just last night I came up with an idea for an alternative propulsion scheme that uses non-Newtonian ferrofluid, which there's a version of that called magnetorheological fluid or something like that. Basically, you suspend a bunch of iron nanoparticles inside an oil, and then when you apply a magnetic field, those particles can line up. Well, you can have dynamic magnetic fields that causes those particles to be flowing around very turbulently, and all that turbulence, you can then alter the magnetic field to basically freeze them in place. And so all of that chaotic turbulence can then be turned into momentum by capturing, by freezing, by changing the viscosity of the fluid very rapidly in a specific direction. Might be a there, I don't know yet. All right, let's do some Tesla coil stuff here. I forget what I was going to do with the Tesla coil, so give me a moment while I remember. Anyone want to remind me what I was supposed to do with Tesla coil? Nathan, if you're on here, if you want to give me a reminder about Tesla coil. For now, what I'll do is, here's what I'll do. I'll see if I can't get the camera really close to the scope over here, so it's a lot easier for you guys to see. So pardon me a moment while I move the camera around. There we go. All right, pull this forward as much as I can. All right, I hope that is somewhat more visible. Okay, so right now I will point the camera down so you can see my very messy bench. So this breadboard over here is the breadboard for my tachometer circuits for the optical sensors. So I've found that I can monitor the Tesla coil output via the ground wire of that optical sensor, which is about 3 to 4 inches away from the center disk. For the purpose of this test, though, to remove any doubt, I will take the probe and I will attach it. I will attach it to the center disk, directly to the center disk. After I turn my attenuation up as much as I can. There we go. Oh, geez. There we go. All right, so now you can get some more legitimate readings. And I need to see, am I actually on the 10x setting for this? No, I was on the 1x setting, that's why. All right, 10x setting. There we go. So fundamental frequency, 748. I'm getting a reading of about a dBm, which, if y'all are curious, I can change that to millivolts, which that is 48 dBm volts. Not dB millivolts, dB millivolts. Let's just go to watts. So that's 1.3 milliwatts is what I'm getting on that. But that is with the 10x turned on. If I go to the 1x, there we go. You can see that that's actually 40 milliwatts. I'm going to keep it on 1x for now so we get better readings. So 40 milliwatts of RF coming off of that. That is not a lot. my ham radio down here can put out 100 watts of RF, and I have done tests at 14-ish megahertz, where I've gotten really good results. 14 megahertz at 100 watts versus this is, 3/4 of a megahertz at, 1/3 of a watt. No, not 1/3 of a watt. Sorry. 1/30th of a watt. Is that right? I need more caffeine. Is there anything special about Alexey's Tesla coil? I bought one with a control dial. Yeah, actually, here's what I'll do first. Let me show you the circuit for the Tesla coil. Turn that off for now. Yeah, give me just a minute to open up the box for the Tesla coil, and I will point the camera down inside there. And we'll see if maybe I can shed some light for you all. Let's turn on the power to the thing before I open it. All right. goes one screw. I hope you can see just how simple this is, right? We have, here's another screw. We have a 25 volt, 4,700 microfarad rated capacitor. We have one of these, I can't remember my resistor codes to save my life. I think it's a 47 K resistor. Don't quote me on that. I think that's a 47K 5-watt power resistor. Oh, sorry. Having trouble seeing. Let me bend that so you can see it better. Yeah, so this big guy right here is it's about as close as I can bring it. That is a power resistor, right? And then we got our big old pot here, which is, I want to say it's a 10K. Don't quote me on that. I want to say it's a 10K pot. Off the 10K pot, we got another resistor here, which, apologies, that brown, black, black, red. So that's 2, 1, 3. So I think that's a 220 ohm resistor coming off of the pot, going to the transistor is it's the same transistor I think that Alexey was using in some of his stuff. It is a C25770320. See if I can get that on camera very well. Anyways, and then you just got the switch up there. Pretty simple circuit. Anyways, put that all back together. So let's go back to our scope here. There we go. Let's turn back on. There we go. Is there a physical magnetic field created by the Tesla coil? So the Tesla coil, operating at high frequency, means that the center disk now has a skin effect going on. And the skin effect means that internal fields are getting pushed to their surface. So while it doesn't have a magnetic field, it interacts with existing magnetic fields by kind of like expelling the existing magnetic fields closer to the surface. Do you not have a high voltage probe? I do have a high voltage probe, but sadly, a couple days ago, my high voltage probe dropped on the ground and I broke my tip. So now what I've done is I've just started winding the wire around the threads of this thing, the wire for the secondary of the Tesla coil. But pain in the butt using those probes. Pain in the butt. I mean, they're good, don't get me wrong, but I just soon use a 10x probe and attenuate on the scope for now. I don't even use the multimeter. I would highly recommend getting good with a multimeter. Like this tool for anyone working in electronics is like the equivalent of a hammer for somebody working in construction, right? Like, how would you do your job without a hammer if you were building houses? How would you work on anything electronic if you don't know how many volts, how many amps, how many hertz, right? You gotta know what's going on with your circuit, and that is like the quickest, easiest tool to determine whether or not current is flowing, whether or not voltage is present. Highly recommend getting, the basics with a multimeter down pat before trying to embark on any electronics endeavors. I mean, y'all do you, but I'm giving my 2 cents there. All right. Go by sound like Alexey. I mean, yeah, you can, but even Alexey was using a multimeter. You can see in some of his videos, like, he knows how to use a multimeter. Maybe not a multimeter with a frequency function, but he knows how to use a multimeter. If you don't know how to use a multimeter, you're going to have a lot more headaches whenever you build these circuits, because you got to be able to troubleshoot a circuit in order to build a working circuit. If you just follow the recipe, you're going to run into problems. Let's see. Oh, you're a welder. Yeah. Welding is a very valuable skill. Very good skill to have. And if you're using welding equipment, you actually have access to some pretty good stuff. So welders, especially like arc welders, electric arc welders, they have their uses for this kind of stuff. If you have any scrap arc welders around, they're operating at really high current at decently low frequencies. So I want to say, a couple kilohertz maybe. Maybe it's up to like 30 kilohertz or something like that, but you're able to get, 60 amps or 600 amps or something like that from your arc welders, which, yeah, there's a lot of value in old arc welders. And soldering too. Anyways, let's get back to this guy. As I have moved this thing around, it looks like my peak frequency there might have changed a little bit. Maybe not. Let's zoom in on our fundamental. So, stop frequency, bring you down. Start frequency, bring you up. Just going to keep going back and forth until I get this guy nice and big. Eventually, we should get to the point where it wants to walk all around. I'd say that's pretty good. That is a start frequency of 715, stop frequency of 716 kilohertz. Right, so there we go. Because I don't have continuous peak on, you can watch that green spot, which is where it was at when I hit the peak button just a second ago, and we can see it's kind of walking down, right? I hit it again, now it's gone down by, 100 hertz or so. And it keeps kind of walking down. There are a lot of potential reasons why it keeps walking down. One of them might be local electrostatic changes in the air. So, like the ionosphere above you, way above you, creates electrostatic potential even down to the surface of the Earth. So like this is only changing by like, 10 hertz every 10 seconds. It's like a hertz a second. Anyways, so if you have a big old plasma plume up in the ionosphere that's flowing overhead, that's going to change the surface charge all the way down to the ground of the Earth. So it's kind of like that sweet spot frequency of your Tesla coil is going to change whether or not you're testing at peak ionosphere charge or minimum ionospheric charge. Peak charge is when the sunlight has charged it up the most and it's pushed the ionosphere down closer to the surface of the ground. Minimum ionospheric time, when the frequency goes up and the total charge goes down, that is like in the wee hours of the morning, right? So like 1 to 3 p.m. in the day is like peak ionosphere. 1 to 3 a.m. at night or something like that is like minimum. Anyways, Yeah, it's solidly changing for some reason. But all right, so now I'm adjusting the knob, right? Let's put continuous peak on so we can watch our number up here. All right, so I'm gonna have to adjust my window here. So all the way down at the bottom of the potentiometer knob, we're at 715.79 kilohertz. As I adjust the knob to the other end, oh, it's gone way far away. I got to zoom out more. Zoom out a lot more. Let's see. There we go. 713.68. 715.8. So you do have like about a 2.5 kilohertz window there for the fundamental. And I am only turning it, yeah. See if I can back this up so you can see how much of the knob I'm turning to get that. So you can see the majority of it is in the last like eighth of a turn on the knob. And then the first like 3/4 of the thing, you get very little movement. But yeah, up here, and this will also go, I'll zoom out again. This will also go for the higher harmonics as well. Stop frequency, turn me way up. Turn me down a little bit again, stop frequency up. So I want to say, especially if I can turn my attenuation down a little bit. I want to say, yeah. So you can see, I'll hold this up again so you can see how much I'm turning it. There we go. So in the last little bit here, as I turn it all the way to the max, you can see some of these spikes, their amplitude drops at the maximum, while other ones kind of go up a little bit. So let's just zoom in on a couple more of these spikes so you can see how much they're changing. I really want to zoom in on the one that changes the most in amplitude. So that would be, let's see. So that would be this guy up here at 2.86 megahertz. 2.8. Yeah, so this guy up here. So let's see the stop frequency on that. Let's go 2.9 megahertz. There we go. Zoom in on that a little more. You can really see how much it changes when I move the knob. Too much. Gotta zoom out a little more. There we go. That's pretty good. Peak, continuous. All right, so right now I am at 2.82 meg at the bottom, 2.88 meg at the top. The maximum when, let's see if I can keep this up here hard enough you can see it. So I'm all the way counterclockwise on the knob, which is like the minimum setting. I am at it does change some as I move my hands around and whatnot, but we're ballpark 2.86 meg. And at the other end, we're at 2.85. So actually, let me get better numbers for you here. We are at 2.8535, right? So 2,853,000 hertz, 2,853 kilohertz. Now we're at the other end, we're at 2,862 kilohertz, right? Sometimes when you're dealing with the low thousands of kilohertz, right, the single digit megahertz, sometimes it makes it easier just thinking kilocycles. So the overall difference here is about 9 kilohertz from 2.853 to 2.862. And the amplitude difference, we're at 800 nanowatts there, and we're at 200 nanowatts there. And rather than going nanowatts, let's go back to dBm, like I like. I really prefer dBm. So that's negative 37. That's negative 30.5. So fairly significant difference. Remember, 3 dB is double the power, and that's about 6 dB. Let's see. Going back to comments here. I've missed. How do you find the frequency of your test coil with the oscilloscope? Well, let me show you. Let's go over to the oscilloscope here. Let me adjust some stuff. I'm just going to move my probe from the spectrum analyzer over here. Oh, I gotta turn my 10x. Okay, yeah. So I'm probably gonna need to use. Okay, turn you off. There we go. Now I can. My scope is having issues here. Let's see if I can actually type this in. 10 volts. There we go. Yeah, I'm gonna have to use my high voltage probe. So I think I was measuring this before, and I think it was like I was getting 4 kilovolts, which I don't think I'm going to be able to attenuate this that much. Let me try. Go 10 kilovolts. Yeah, no, 10 volts is the upper limit, and it won't attenuate it any more than that. So if you want to test, man, sorry, cannot multitask to save my life. What do I have this connected to right now? Oh. I already got my high voltage probe connected over here. Apologies, folks. Move stuff out of the way. So what I'm going to do is I'm going to take a high voltage probe. I'm going to connect it to the wire on my secondary there. You can get these high voltage probes off of Amazon for, I can't remember. I thought it was pretty reasonable. It was like maybe $60. Technical difficulties. All right, just wind this thing around like so. Is that gonna hold? Okay, I think that's gonna hold. There we go. Okay. So now, when I turn on my high voltage, there we go. All right. So that probe is a 1000X probe, right? So if I turn off these other ones, make it easier to see. Measure. So I'm going to get the peak to peak first. So right now, I'm getting 44. Is that right? I feel like something's wrong there. I'm getting 44 volts times 1,000 would be 44,000 volts. That's not right. I think I got an attenuation setting on here wrong. Anyways, I'm not going to fix it now. I want to show you how to get your frequency stuff. So oscilloscopes should have a function called FFT. They pretty much all have it. And I want to say for me, it's under the measure. Maybe it's under the measure. I haven't used it on here for a little bit, so give me a moment. No, that's not where it is. It's a setting here on the side. Analyze, maybe? Thank you for your patience. FFT right there. There we go. Channel 4 on. I want to say, there we go. Now I'm moving that guy out of the way. All right, so now I have a spectrum analyzer on my oscilloscope, right? You can see all of these spikes, but you can see it refreshes really slowly. That's why I don't like using it on these, because the refresh rate usually isn't good. All of your oscilloscopes should have a SA/S, a sample rate per second. Minimum, you should have a 1 gigasample. Really, it should be a 2 gigasample, or GSA/S. This is an 8 gigasample, and you can still see how slow it's going at 8 gigasamples. Now, there's a way to adjust the sample rate here. I think right now my sample rate might be turned down a little bit. I'm not going to go through how to change your sample rate, though, because that's a YouTube video all in and of itself. Anyways, as I adjust the knob, get this on camera for you. There we go. So I adjust the knob. Should see some of these things. So right now, this is 0 to 2.5 megahertz. Right? So this spot right here is our 750 kilohertz right there. I think I can click and drag this maybe? Nope. There is a way, peak search on. There's a way to be able to do it. I actually have like an older oscilloscope that's a lot easier to use the FFT on. This one is a computer on steroids as far as digital oscilloscopes go. And I haven't played around with the FFT on it enough to even make it useful for me. But as you can see, FFT, you can see your spikes. I should be able to adjust my end frequency here. So this scope can do up to 350 megahertz. But I'm not getting that. Come down here. I start getting something again. Man. Now it's starting to come back. For a second there, I had it good enough that I was able to actually read my peaks here. All right, there we go. Now it's reading my peak at 730.78 kilohertz. And then I got another one there for a second that is 1.4615 megahertz. And it's giving me an amplitude in dBV right now, which is reading at about 10 dBV for the 730 kilohertz, give or take. Can I change that scale in dBV? No, I cannot. It's just going to give me dBV. I don't know. Oh, unit. There we go. I get VRMS or dBV. That's lame. All right. Yeah. I'm not going to play around with that a whole lot more, but I would highly recommend typing in your model number of your oscilloscope into YouTube and FFT, and if nothing shows up there, when all else fails, RTFM, right? You can find a PDF of your scope manual on the internet pretty easily. And there should be a chapter in there, usually, or at least a section about using the FFT function. And once you spend, a good hour, usually is how long it takes to play around with it to get good at it. And as you can tell, I haven't even spent the hour to get good at using mine. Let's see. Going back through the messages here, see what else I've missed. Daniel Foster, yes, FFT is fast Fourier transform. Yeah, you're okay. So Anthony is saying that these coils should be about a megahertz, like 1 to 7 megahertz, since primaries are really short. So these kilohertz frequencies are only harmonics at best. Yeah, so it's interesting that I connect this back up to let's go over here. Get my frequency back down to readable amounts. Stop frequency. Shebang. There we go. Actually, I'll scroll that up a lot more so you can see it. So I will have you notice that this first peak that we get here is our 730 kilohertz, right? And every peak after that, and it's like, 1 dBm. And then every single one after that, peak not continuous. There we go. And then the next peak we have at 1.47 meg is negative 38 dBm, right? Remember, this is a logarithmic scale. So we've got a really loud signal at 730, and then all other signals past that are super quiet. So, and it's a self-resonant circuit. I think part of the reason why this 730 is the main harmonic that it looks like you get, I think part of that is due to the capacitor that is being used in this circuit. I want to say when I used other capacitors, I was able to get the 1.4 to be the primary, but this is the way Alexey had it. So that's the way I got it. Let's see if I can span out on this a little more. You guys can really appreciate how many harmonics there are. It is not insignificant, but it does stop. Well, I shouldn't say stop. Like there's still more way up higher. Especially if I lower the amplitude. And it's going to start screaming at me. I need to get my reference level lower. Attenuate. Yeah. Quit whining. All right. So if I actually measure on here, the 10% mark of this last hump is at 40 meg, right? But I mean, we're down in the noise floor. We're at negative 63 dB. I wanted to get this guy 40 megahertz. There we go. So now you can see all those harmonics again. As I adjust the knob, can you see that on screen? There we go. As I adjust the knob, especially in that last quarter turn, you can see how we get a big change in all of this, which is 20 megahertz at the center, 40 megahertz at the end, right? You can see how we get a lot of change there. But like that's down at the noise floor, right? How can something that is such a quiet signal really be affecting anything? Although I will say that it is also at those amplitudes down here where the beat frequency of the spinning discs seems to have a big interaction happening. Okay, fine. I will turn the amplitude way up higher. We should make you happier. There we go. That should be better. All right. I think I am at the 2-hour mark, so I'm going to start winding down here. One frequency shouldn't be random. Yep. I think that's what I got for today, folks. I'm going to end up putting my Graviflyer rotor back together there and do some more testing. I feel pretty good about that state that it got into. It got into a really nice resonance state today. I haven't gotten this new Graviflyer into such a sweet spot. Yeah, like at all. Like that's the first time since I built this thing I got it into such a great resonance state. So I'm excited to put it back together and keep testing. All right, gents and ladies, if there's any, peace out.